And we will go on to the next presenter, and that should be Mr. Tenorio. Are you here? Yeah.
Yes, I am here. Let me check with Marc.
Yeah, I'm here and ready to go now. Thanks for your patience with me.
So
Okay.
you will talk about the extraction of icy regolith from a crater at the permanently shadowed regions of the lunar South Pole using a sandwich conveyor system. And you are both in Arizona, right? Or no? I let you introduce yourself. I wasn't read up properly there. Over to you. Thank you.
Okay, let me start here. Thank you, Niklas, for the introduction. Actually, this is a great opportunity for us and a privilege to be in the Lunar Development Conference this year. And also, we are pleased to present collaboration and innovative technique or approach for extracting material from the moon. And I would like to introduce first Marc dos Santos. Marc, okay, and yeah, we are in different time zones, but I think you are in Georgia, is that right?
I'm in Marietta, Georgia, yes, just outside of Atlanta.
And we manage the way to work, remotely and do this. And also, we'd like to introduce other authors, Dr. Muhammad Waqas, also working at the University of Arizona, and student Matthew Patterson. So let's start with this. Basically, we're going to show an approach for working at the moon with technologies that are already working and tested on the Earth, and they should be ready for with minor modifications to work on the moon. So this is a very hands-on approach, and we try to do it as if we were already up there at the moon. First, targeting the areas where we are finding water. We're mainly working in extraction of icy regolith, but this could be applicable also for other materials that we will find mainly around the crater, the ejecta, nickel and iron, and other materials that, as we have seen in previous presentations, will be relatively abundant in the south pole of the moon and other parts of the moon as well. Focusing on the south pole, we already know about the Aitken Basin, a very mysterious but also attractive area for finding water and other materials. It's bombarded by many craters, and we know that its position is kind of telling us a lot about its the permanent shadow regions that we have there, and the craters that are permanently in the darkness. And with that said, we have here, this is from Moontrek, a visual of Shackleton crater, one of the most notorious features at the South Pole, and then the South Pole itself and the rim of the crater. And we are focusing on an area that, among many, because we started around Shackleton, we're focusing on this area of interest, which is called the Shackleton-de Gerlach Ridge. It has several other names, but that's, I guess, the final name on this. So this is a very notorious chain of craters, and we are focusing on one of them. So we're using other tools from Moontrek that is basically different layers. This is from LoLa, DEM, South Pole 10M Coral Hillshade. Basically is the lunar orbiter, lunar reconnaissance orbiter, laser altimeter, and the digital elevation model. We have different colors, and these colors are more or less in every 1,000 meters. So that means that the crater that we see, the bottom of the crater of Shackleton, that we can finally see it, is 4,000 meters deep and goes all the way to the thousands on the surface. And we'll see that with other tools. This is from the El Rock or ACTL Rock. This is from Arizona State University. it's a very nice tool that also give us names of some of these craters. And we focus on one in particular, one in the middle of the ridge that is called Worthy, and that will be our target destination. So let's jump into the essentials. I mean, we are going to focus on mining, but we would like to kind of getting acquainted with our neighborhood. Here's where we have the Shackleton de Gerlach Ridge from a different perspective, a different view. We can see now the South Pole down below the crater, and Worthy in the middle of the ridge here. Well, it's a permanent shallow crater. There's an actual view of it, and we have targeted the center of the crater, and those are the coordinates if you want to look after the treasure map. Well, looking at some geology, we see here, this is also from the orbiter camera, and I have a zoom here to show you details of the crater itself. It's kind of irregular. The shapes are kind of deceiving, but at the same time, it's giving us more or less the nature of the crater. So we have two types of material: intensely slumped surface, the bottom, and moderately slumped surface. So these are materials that perhaps after crater hits and the let's say the exposure to different extreme heats, we have at the end regolith, abundant regolith, and most likely water trapped on it. We are not thinking of the metals. That will be an added value of our extraction, but basically we want to work on how to extract these materials from the bottom of the crater. And this is a perspective view. Also, now we know the places like South Pole and the ridge itself. This has a little bit of perspective, but we are aiming to land on site 001. And we'll see here, this is Worthy, and our moon base will be located at this position, more or less a flat area. And I would like to kind of refer to some of the things that we have seen in previous presentations, like the Andrew's mining nodes from the All Matter machine, sort of an inspiration of that, and a landing site for working. And there's a few more here. So yes, once that's the road, that's the commuting road for going to our work. We have a safety distance of 3 to 5 kilometers for avoiding dust, vibration, and fly rock if there's any type of activity breaking the rocks or so. And once in a while we can go back to home and return. Well, the lunar topography, and this is where we have aimed more. We were more focused. We obtained that also from one of these tools. These are every 100 meters. Okay, and we will notice that our target area, this is assuming in where we can see where it is more or less in the 1700s. And so we are good. We're not lost on the moon. These are the correct coordinates. And then we move this to QGIS, and this is a BC graph, and it's very valuable because the contours are every 1 meter. We tried with contours every 5 meters, which is every 10 and every 5 meters. They are okay, but at the end we need something more minute because we are going to work by the meter, even by a fraction of the meter. And this gives us a sort of views of shades and the shape of the deposits. The lines that we see there are artifacts from the Lunar Reconnaissance Orbiter, but we can ignore them and work with the actual contours. So there's Worthy, and this is assuming in where we still see the shape and the features of Worthy, and we're still 1 meter contours, and we are going to also mark the major sections that we will be using. Given the nature of this technology, the sandwich conveyor technology that is going to be presented, any profile is okay. So that's not the major challenge, but the important thing is that we can have a stockpiling area at the rim of the crater. And here it is, some of the main profiles, the 4 profiles that I've shown, some vertical exaggeration, and it will be the beginning of their work. Is these peaks that we can see here are the artifacts that we need to kind of ignore because we can smooth them out for the actual work. And from here, I will going to enter into Regolith conveyance. I would like to let first talk about what we're going to see in Regolith conveyance, basically the design of the system and the challenges that we already know on the surface of the moon, including profile, the illumination. This is going to be dark all the time, and the constitution of material, how hard, how big the fragments are going to be, and other things like power, heating, and production rate. And this is a simplified view of the Regolith using the sound velocity and the simplified version that was used by NASA for Break the Ice Lunar Challenging, where we participated and makes things easier in terms of abundance of water that we might find. This could be different at the bottom of the crater. We may have other metals or maybe the core of the meteorite or asteroid, the meteorite that maybe have hit on the bottom of the crater or so. And some behavior of the natural angular repulse of material. Even better if we are going to make ditches, berms, or other features. Here I would like to give the word to Marc for this part with the Santos conveyor. Marc?
Okay, thank you, Dr. Tenorio. Thank you to the Moon Society, too, for accepting me as a member. I'm excited to be here on this anniversary. It's really neat that you guys set it up to correspond to the anniversary of the landing. Dr. Tenorio, I do want to make a last minute switch, and if you could take me to my third slide first, the
yes.
Y sandwich belt conveying. I think it just flows better if we do it that way, because you may all be wondering why am I here? I'm a conveyor guy. My background, I actually have an aerospace engineering degree, but I've been terrestrial for most of my career, working on materials handling equipment for mining and plant applications. But so why sandwich belt conveying? I know somebody earlier today mentioned conveying on the moon and mining equipment being used on the moon and what the implications would be for that. And I want to fully admit that I don't have a good, deep understanding of what the implications are. So what I'm presenting here takes a lot of terrestrial technology and turns it into what I think can work on the moon based on other things that I know work on the moon. But the reason for sandwich belt conveying is on Earth, we use them for high inclines and high lifts. The material gets sandwiched between 2 belts and can carry at steep angles. There's locations on the moon where I believe that will come in handy. Deep craters with steep walls will require that capability. But sandwich belts are going to be appropriate even at low or zero angle applications, because a conventional open trough conveyor will likely lose its material due to disturbance over the idlers. It happens on Earth that material jostles out, it bumps over idlers, and it gets released and falls outside of the belt. And that's a standard thing in mining. On the moon, with the reduced gravity, I believe it will be much worse. So an open trough conveyor, I don't believe, is an option in the low gravity. Pipe conveyors might be pushed as a solution, but they really won't work either, because they're going to struggle to carry a consistent stream. The material will just jostle around within them. Sandwich belt conveyors, on the other hand, will gently hug the material through the path, successfully carrying that material to the destination. So let's go back to my first slide, and I'll tell you a little bit about sandwich belt conveying, because unfortunately we don't do a good enough job of marketing it, and there's a lot of people who are not familiar with it. So a quick primer on the technology. Sandwich belt conveyor carries material between 2 standard conventional conveyor belts, hugging the material into the sandwich by radial or applied pressure. Radial pressure is achieved by reversing curvature along idlers through the conveying path. You see that on the left side of the slide. Applied pressure is achieved by a spring-loaded, fully equalized mechanism. And each method works equally well to hug the material. It applies only the pressure that will develop the internal friction of the material, and thereby stop that material from sliding backwards in the conveying path. So in both cases, that pressure is achieved purely by mechanical means, and I don't believe that gets affected by reduced gravity or a vacuum environment. Next slide. The hugging effect, when you combine it with the proper sizing of a material cross-section, ensures that there's ample belt-to-belt contact along the edges of the sandwich profile to account for any belt misalignment that naturally occurs. The sandwich profile shown here has a load of material running through it, but as the material load decreases, the distance between the belts also decreases until the belts are face-to-face at zero load. In this way, a gentle, consistent hugging exists in all loading scenarios that's set by the tension you apply to the belt. So now we'll jump 2 slides to the Warty crater. Yeah, and so I chose the slice of the Warty crater on Moontrek to run our conveyor along, and I got this elevation profile. Like Dr. Tenorio said, this isn't necessarily the optimal path. We would figure that out just like you would do in a typical mining application. What's the best path? But the sandwich belt conveyor will run along whatever path is chosen, and it will carry material at any angle. So as you can see in the conveyor path, if you can see it, if your screen's big enough, it's indicated in red along the profile of the crater, and that is to scale. I squashed the vertical to get it right. So it hits about 20 degrees at its steepest angle. But in any case, it's appropriate to continue sandwiching the material throughout the path, and we can continue on beyond that point as well, beyond the rim of the crater with the sandwich conveyor. So next slide, please.
One sec. Yeah.
Okay, so as I said, I don't have really deep knowledge here. I've fallen away from my aerospace roots and been working on Earth way too much, and don't have the deep knowledge that I should. But I want to keep working on this. Dr. Tenorio has been a great inspiration to me on this, and I really enjoyed working with him. He gave me a Acta Astronautica paper that talked about regolith conveyance, and I referenced that quite a bit. So I took what they assumed to be possible on the moon to also be possible with sandwich belt conveying. So I then went around to suppliers and I talked to them for the equipment we would typically get. So for belt, I was told by a major belt supplier that they have developed a polyurethane type of material for tires that can handle the lunar temperature range. The material dictates that our curves are somewhat larger, but that's typical in mining anyway. We often open up our curve radii on mining. We'll do it on the moon as well. Idlers, pulleys, motors, reducers, and tensioning systems. I don't know of any that are immediately available for moon operation, but I'm confident that with the other equipment that has operated in the lunar and space environment, that we can come up with the right add-ons to that equipment to get it operating well. The belt cleaners are typically a plasticky material. Most likely we would use a metallic type material. Safety controls I know exist in the moon environment. We would use similar. And for the structure with the reduced gravity, I expect lighter materials can be used. Aluminum, titanium, those are probably good candidates. They reduce the cargo weight to be transported, and they'll still support the conveyor components. And we'll arrange the structure in a collapsible accordion type arrangement to the extent possible. A conveyor lends itself well to that because the idlers are usually spaced a few feet apart, so you can collapse structure. That little conveyor I show there is a more of a package handling system, but to use that kind of a concept will work well, I believe. Next slide. So on basic sandwich belt parameters, yes, we chose to size the conveyor to carry a volumetric equivalent of 1,000 tons an hour of regolith at the lowest bulk density. And I saw somebody on a previous had a lower bulk density for regolith, so we would need to test that and make sure we're doing it right. But around 1,000 tons an hour, I think, is well within what we're going to need to do in the stuff we were talking about doing. It's well handled by a 1,200 millimeter belt running 2.4 meters per second. And I think we may actually want to slow that down a bit in the lunar environment, but that just takes some testing. The material should be reduced down to around 200 millimeter lump size for this belt width. And so you need a crusher in the base of the crater. And that is totally out of my scope to figure that out. But I believe something can be developed that way as well. The tension forces in the belt applied the same way on the moon as they are on Earth, but the values will be lower since we're hugging a lighter weight material. And like I said, the belt will be similar to a steel cord belt in its behavior. Drive power is pretty modest because of the reduced gravity. And then the important part, going back to what Madison was just talking about with the cost to get it up there, my goodness, 114 tons it's not going to be cheap, but hopefully by the time we're running this up there, it's going to be a good bit cheaper than that 1.2 million. And volume of the idlers, I think, comes out to about 160 cubic meters. Then you have steel on top of that, but the craft that I think Dr. Tenorio shows in a later slide gets us about 1,100 cubic meters and 100 tons. So we're going to be over on weight before we're over on volume, I believe. And it's just a matter of packing things carefully. I do a really good job packing the trunk when we go on trips, so I think I can come up with something good. So let's do the next slide.
Yes.
And so there's a lot more detail I'm sure I could come up with, and I do look forward to working more on this and hopefully being here again next year for future Moon Society events. The chart on the right side just shows a parameters table for the sandwich belt conveyor we would propose in this application. Electrifying would be achieved the same way as any other fixed or driven equipment on the moon. The only point that really needs power is at the head end where the drives are. There are safety switches along the length, but in this environment, I expect we'd have solar and battery power and wireless communication for that. Control of the conveyor in an Earth environment would be at a plant PLC. On the moon, I think we'd, again, go a lot more wireless, get to personal devices and an app of some sort. The conveyor needs to be loaded by something that gives it a metered flow, like an apron feeder or similar. It can comfortably carry anything between zero load and the full design load. The discharge arrangement, I know Dr. Tenorio has some slides on that as well. That'll be based on what the material needs to do next. If it needs to be segregated, it can go through a split chute, or it can just continue on directly to a processing facility by continuing that sandwich arrangement over the lunar surface. Installation and assembly just needs to follow best practices that are used for other lunar structures. We'll make the equipment as modular as possible so it can expand from its shipping state and go right out into the full-length configuration. If we put down some sleeper-type foundations, the structure can just be mounted to the crater wall, belt spliced, drives electrified, and then the system gets started up. And based on the schedule we've discussed, I've got a couple of weeks blocked out for the startup visit to the Wardy crater, so I definitely look forward to making that trip. And so that's all I have to add for now, and I'll pass it back to you, Dr. Tenorio.
Thank you, Marc. I guess we still have some minutes. Just for the basic things, well, shipment is one of the big issues. It's a section of the Starship Lunar, and here we have it better. 100 tons or 1,100 cubic meters. That means 1.5 trips, so 2 trips, and we can include there the material, the other type of equipment for moving material. And for the equipment selection, well, our favorite workhorse will be the IPEX. We know that this will be at the end limited to its size and capacity, but we can have several of them and also create a sort of a convoy of these units. It has several features that we already know because it's now in TRL5. These are all specs, but they are still valid for that. And with that said, we can have also the Astrobotic. Astrobotic now is one of the new favorites. The Moon Digger would be great for dosing the material. Our production plan, and I'll make it very succinct. This is a simplified view of Wardy, and this is the way the sizes: 600 meters, 200 meters at the bottom, and the 40 meters of height. And then we'll have the road first. That will take 3 months. The deployment and recharging will be taking more or less 1 month with backup systems and so. The conveyor belt and its sleepers and all the infrastructure there. And also the strips, the mining units. We call it the RMUs now, Regolith mining units. They are very specific, 10 meters times 1 times 1. And we can see them doing that. And finally, we will be having the system working. And once we have that, repeat 5 times means 5 meters. That's our goal. We have to make some measurements. There are some calculations by Dr. Waqas that I'm going to show. This is another view on the top, very busy, but I'm using the north-south as an example. uh, uh, and the mining units there. So we can have evens and odds and make this kind of staggered and make the stockpile at the top. And then those of the materials after some selection of the different types of water content. The mining Regolith, the RMU, trying to mean that the Regolith mining unit is 10 meters and is more or less half is the width of the equipment, which is almost half meter. So that would be kind of a discrete way of moving it. We have to add this, the distance, the time for mining, and also the time for dumping the material in the front of the apron feeder or whatever it is for reaching the conveyor belt. And then this is another view of, in this case, I use an example, the north-south profile, some vertical exaggeration just to show meter 1, meter 2, meter 3, meter 4, meter 5. So they never are regular, but let me go back just to show the entire thing and the accessories for feeding and also dumping the material. And the production planning, this is things by to Dr. Waqas. This has been done for one mining unit and with one IPEX. So we have to add here, if we have two, we can double the capacity, and we have four, and so on. We can have this moving this material. For the moment, we're moving this in thousands of kilograms. Hopefully, we can get a quota for the entire year of operation. We have to decide whether we're going to work in daylight only or all the time, because it's always dark inside the crater. And these are basic economics in where our budget will fit. Here we have the demand in 100 million tons per year, I guess, and with a cost of 7,500, we have to believe some Arriba's numbers for this. And finally, or in our conclusions, these are us four. These are the advantages of using the sandwich conveyor belt. We have heard things like the bucket wheel excavator and other ideas that are very possible and malleable. It may fall in the middle of this depending on the scale of operations and how this is going to grow. And a cost estimation, we use Elon Musk's number, $10,000 per pound. But hopefully that makes it this feasible 2.5 billion. If we go down and make 5 billion on this, we are paying back the technology and installation. I know this is very, very basic, but at least it's giving us some idea of what we're doing. And we have minted this as Project R Scoop, R again for Regolith and sandwich conveyor operations for overshadowed polar regions, and a sort of a motto here: scalable, efficient, and economically viable ISRU solution for the moon. With this, we are finishing. This is the concept beyond that I put in the abstract, but this is an actual Dos Santos sandwich conveyor belt adapted to one earth mount. We know that this exists as a crater for testing with simulant, and some machines, different brands, the Clipex there, and other brands that we would like to have to make this more efficient, and then move to the next crater and complete our work there. Yeah, so, and these are some of the citations we have used, Arc Astronautica, some papers, white papers from NASA, and a couple of interesting sites that have great things to learn from. So this is what we have so far. Thank you for the timing, and thank you to our co-authors, Marc, Dr. Waqas, Matthew, and this is all what we have today.
Thank you, Tito. And you did it in exactly 30 minutes, but since we have one presenter who hasn't turned up yet, we can have a couple of short questions if there are any.
I have a question.
Thank you, Stuart.
Right.
So did you consider, instead of the conveyor, did you consider simply accelerating the material and getting up to about 90 kilometers per hour and then just putting it into a trajectory so that it goes up to the top of the rim?
That was actually spoken about in that paper that I referenced. They considered that as an option, and they considered projectile, they considered conveying, they considered I think, trucking, like the equivalent of trucking, and they found the conveyor to be the best, and they didn't have the sandwich conveyor in consideration at that time. So they had the negatives of open trough conveying considered, which actually brought that down a bit. And I believe I'm in touch with the guy to try to rewrite his paper, sort of, but to just to advance it. And I believe with it as sandwich belt conveying, it makes it an obvious. But that was presented, and it's certainly an option. It's certainly a viable option.
Where's that paper? What was that? Where was that?
I hate to put off the guy doing the dance
let
there.
me put it back here.
Yeah, go back one.
This is the one.
Yeah,
Kevin
that one.
Cannon. Well,
Kevin McCann.
Patterson
Okay.
196. Yes.
Thank you.
Okay. And to fill the technology gap there, I mean, they're talking about conveyance of different types, but this is the first time it's mentioned the sandwich conveyor and its features and advantages.
Yeah, I think bucket elevators were another
Yeah.
consideration, and they just fling the material way too hard, and it's more brutal on the material.
Yes.
Okay, thank you. That seems to be running out there.
Excuse me,
Yes, Frida.
what happened to the concept that space was going to be very, very valuable for making things that required low or zero gravity? In certain crystallization processes that would be more perfect with lower gravity or zero gravity? I haven't heard anybody address that. Okay.
You're not asking specific to our presentation. You're just saying generally.
It seems to me that mining, I don't know what that noise is. It
Yeah,
seems
it's
to me
not-
that mining is the least efficient. I mean, you're taking huge amounts of raw material to get small amounts of what you want, and then you have to purify it. It just seems to me that there would be processes that would be at zero gravity or lower gravity that would be much more economically feasible, but I haven't heard anybody discuss that possibility. And I'm just puzzled that mining would be the first thing that we would look at. And would the price of things like platinum drop if it became extremely abundant?
I think we have Jim. Do you want to reply to this? Otherwise, I think we can move this possibly to you afterwards, or otherwise, just complain to me because I put this session up.
Yeah, this session is on mining and utilization of lunar materials. In the work that's been done on crystallization and such, that has been focused on lifting materials from the Earth to space station, then working with the space station in zero gravity to come up with potential products that could be made there. But it's never, with these materials though, it's very small amounts of materials, very high value. I mentioned pharmaceuticals, electronics, crystallography is more in line with the medical work. So it kind of fits the pharmaceuticals. So that's the reason why you haven't heard anything. The focus here is utilization of the lunar materials and not simply launching materials from Earth to make to have cost-effective material, basically cost-effective products.
Thank you, Jim. Very, very good summary answer. And I think we cut this session for now and continue with the